Thank you all for coming today. Welcome. Today we're going to talk about maximizing the value of profile roughness with GelSight. Roughness is a great application that we hear about a lot, and we have some interesting things to tell you about how to use GelSight to measure roughness. First, we'll start with some introductions. So I'm Kimo Johnson. I'm co-founder and chief science officer here at GelSight. Back in 2008 through 2011, I was a postdoc at MIT where I worked on the GelSight technology with Professor Ted Adelson. And then in 2011, spun the company out. We've been at it ever since, growing new applications for this, seeing this technology get out into the world. I'm joined today by Abby Lindberg and Patrick Stack. Abby, why don't you introduce yourself?
Hi, I'm Abby Lindberg. I am GelSight's lead applications engineer. I've been in the machine vision industry for almost a decade, and at GelSight right now, I do anything customer training or support or application development.
Thank you. And Pat?
Yeah, my name is Patrick Stack. I've been with GelSight for almost 2 years now as a principal software engineer. Prior to that, I've been writing surface metrology software for over 25 years now. And at one time, I was a member of the ASME B46.1 Standards Committee for the classification of surface texture. So I've been doing this for quite a while.
Great, thank you. And Pat is our resident expert on all things roughness, parameters, and things like this. So we're happy to go into it today. We'll go deep into the math, get an understanding of how different parameters affect the roughness result. These are a lot of questions we get from customers. Where to draw the line? Does the direction of the line matter? What's this thing about lambda cutoff? And how do I choose it based on my specimen? And so the goal here today is to provide some intuition for how these parameters affect the roughness result, give you an idea of what the math is doing and how to think about the type of signal that ends up in the roughness signal versus the waviness signal. And then really to emphasize that a lot of these decisions come back to an understanding of the component, understanding its form, its function, what it does. But this should at least give you a flavor for how to choose the right roughness parameters when you're doing the analysis. So on the next slide, we show a lot of examples that we've encountered. And why do we need to measure roughness? Why do customers need to do this? What applications is it interesting? A lot of times it comes down to the function of the component. If you have two components that mate and need to make a good seal, there's often a roughness spec. And if the part is out of spec, maybe the seal won't be as good. Or in applications of abrasives, the roughness itself will dictate how well the abrasive works. Over time, it will get smoother. And if you monitor the roughness of the abrasive, you can tell if it's past its working life. In the space of paints and coatings, or in composites that need to be put together in their worry about adhesion, the surface roughness is a critical parameter in all these applications and needs to be monitored and measured as part of the process. But then we've also encountered customers who have a roughness spec that's more related to cosmetic issues, the appearance of the component. And for all of these reasons and more, people are interested in surface roughness. But the thing about roughness, profile roughness or surface roughness, is that it's not as straightforward to measure as something like a hole diameter or a length or a width. And there's a bit of understanding that needs to go into the choice of parameters and how to do the measurement such that you can get a repeatable, reproducible measure. So we'll start with a motivating example. And Abby will switch over to our GelSight mobile software and show a common machine type surface and look at how we do profile roughness on this surface. Abby?
All right, thanks, Kimo. So I have here the FlexBar roughness standard. Basically, we've just got a bunch of different types of machine surfaces with different roughness values. Some of you on this call may have seen this or even have one of these plates before. We see them pretty often. But we're gonna look at the turning N10 patch on this plate. So I'll just go ahead and with our GelSight Mobile Series 2, I'm just gonna take a scan of that patch. So we'll just press down and click the button to take the scan. And once the 3D data is generated, we can perform some analysis. So I'll just open up this one we just took. And the first thing we can do is look at it in 3D. And we can see a model of our surface here. And we could jump back over and let's add a profile roughness function. So for this, I'm just going to draw an input line perpendicular to the lay of our surface. And we can see the output. We've got our RA and we've got some other R parameters here too. Now at the bottom, we've also got the profile. So we have our primary profile, our waviness profile, and our roughness profile. So we can see all of those there. Now, we also have an input here for filter cutoff. And right now, by default, that's set to 0.8 millimeters. So let's change that to 2.5 and click Analyze and see what it does. So we can see the RA went up to 20 micron. And we can take a look at the profiles down here again. We've got the primary waviness and roughness profiles again. So the question might be now, maybe Pat, you can help us answer it, but what filter cutoff should we use for this type of application?
Oh,
Great, thanks, Abby.
it's a good question. Yeah, you can see, we're going to start with a simulated scan, just to keep things simple and straightforward, and it's easier to explain when you have a simulated surface. This particular surface was generated in MATLAB, and it has 3 wavelengths. It's 4 millimeters, 0.1 millimeters, and 0.06 millimeters. Now, on the next slide, you can see that we use the Gaussian filter that we talked about in the previous webinar to separate the roughness from the waviness. Now, the roughness is the shorter wavelength components, and the waviness is the longer wavelength components. The lambda C filter cutoff wavelength is where we differentiate between roughness and waviness. And the primary profile is the actual measured profile extracted from the scan itself. So there's no Gaussian filter applied to the primary profile. So on the left here is the primary profile, which has the 3 sine waves or the wavelength components that we talked about. And you can see that there's a long 4 millimeter wavelength that causes that long undulation. Now, the bottom right is the waviness profile. So that's the wavelengths that are longer than, I believe, 0.8 millimeters in this case. So you can see that one single sine wave in that profile on the bottom. And the top profile is the roughness. So that's the 2 shorter wavelength components combined. So if you were to add the roughness and the waviness, you'd get back the primary profile. So the actual output of the Gaussian filter is the waviness profile. And then we get the roughness by subtracting that from the primary profile. Now, this is kind of another view of those profiles. This is in this, like the frequency domain, or I like to think in wavelengths. So if you look on the left-hand side there, there's 3 peaks in the signal that correspond to those wavelengths we talked about. The 0.06, the 0.1, and 4. Now, in the lower right, you can see that that is the filter, the waviness filter allows only the long wavelengths larger than 0.8 millimeters. So all you're left with is that long wavelength component. And so you see the spike above 0.8. Now, in the top right is the roughness. So everything longer than 0.8 millimeters has been removed from the signal. And the roughness only has the wavelengths below that. So you still see those 2 spikes at 0.1 and 0.06.
Great, thanks, Pat. So this just gave some intuition for how that lambda cutoff creates a filter that splits a signal into the waviness and the roughness components. Now we're going to return to a GelSight mobile and show a measurement on a real specimen. This is a common specimen that we often see in the field. Customers have it because it's a easy specimen to get a hold of. Can come with a certificate, and it's a fairly simple specimen to understand.
All right, so I'll open up this scan of one of the mid-Atoyo roughness standards. So yeah, as Kimo mentioned, we see these a lot in the field, so this might be something that you have. But I'll zoom in a little bit so you can see kind of the period there. So I'll go ahead and I'll add a profile roughness function, just like we did before, perpendicular to our surface texture. And we can see the RA output from this. And we were talking about those wavelengths. So I'll go ahead and add, I'll zoom in here, and we could use that ruler tool again to measure basically peak to peak on this. Something like pretty close to that.
Yeah, I just want to point something out that one of the parameters that we compute, the RSM, actually that computes the average spacing of the peaks in the profile. So you can see that's right at 100 microns, which is what would be expected on this mid-Atoyo plate.
Yeah, and then we can see the primary and waviness profiles associated with this profile roughness function as well.
Now you can see if you take the primary profile and then subtract off the waviness profile from each data point, you end up with the roughness profile.
Great, thank you. So we'll go back to the slides, and we've done a frequency analysis of this as well, so you can get an appreciation for how that filter is working, what it's attenuating, and what it's preserving.
Yeah, this is a MATLAB analysis of that same or similar scan of that mid-Atoyo plate. You can see the sine wave on the top of the image, and that corresponds. The frequency analysis corresponds. There's a spike or a peak in the signal at 100 microns, just like we expected. But there's also a spike at a longer wavelength, and that's the actual tilt of the specimen itself. It's a long wavelength component. That's not uncommon. If we put the sensor down and it's not totally perpendicular to the surface, you're going to have some kind of angle to the scan. And this same thing happens in profilometry. So when the profiler drags a stylus across a part, the part is never exactly level with the datum of the profiler. So you have the similar effect where you have to level the surface. So the Gaussian filter will actually remove that long wavelength. And I think the next slide might show that, I hope. Yes. So you can see there that tilt has been removed by the Gaussian filter because everything longer than that 0.8 wavelength has been attenuated.
Great, thank you. So now that we've built up some intuition for this filtering step, the choice of lambda cutoff, how it splits a signal into the roughness wavelengths and the waviness wavelengths, we can return to the example that we started with, this turning sample, and try to understand why we get such different results when we change that filter parameter.
Yeah, you can see I drew a ruler on the scan image just to show you the distance, the peak-to-peak distance. I had to eyeball and I dragged from pixel to pixel, but it's roughly 0.7 millimeters. So keep that in mind when we analyze the surface. So here it is in MATLAB again. The top profile is the roughness profile. So it's had everything removed, all the wavelengths removed from the primary profile. In this case, it's 2.5 millimeters. And the reason we chose 2.5 is because if you notice, there's that spike at 0.7 millimeters. And that's that pattern. It's, all profiles are made of a combination of sine waves. So the predominant sine wave or wavelength in this particular measurement is at 0.7 millimeters. So setting the Gaussian filter to 2.5 millimeter cutoff allows that particular wavelength to pass through into the roughness profile. Now you can see here once again, you can see the primary profile, which is the actual kind of the raw data, the profile that's been extracted from the scan, and then the waviness profile that we computed is displayed over top of that. And then here is the roughness, which is simply the primary minus the waviness. It leaves you with the roughness. Now, if you look, the RA value here is 22. All right, so keep that in mind, because the next step is to analyze this with the incorrect filter cutoff at 0.8. And what that does is it's so close to the 0.7 millimeter wavelength that we're interested in, it starts to attenuate that signal. So you can see that the amplitude on the top image, the amplitude of that profile has been reduced dramatically by roughly, what, 50–60%. And that's probably not what you want to do. And you can see here that waviness profile was starting to take the general shape of that surface. And that's, in most applications, that's not what you want to do. You want that general shape to be included in the roughness profile. So you can see that this scan is analyzed with a 0.8 millimeter filter cutoff. And if you go to the roughness profile, you'll see that general shape is still there, but the peak to peak amplitude has been reduced dramatically. And the RA value is now 13, which is roughly 60% of the 20 that we saw with the 2.5 millimeter cutoff.
Great, thank you. And so it's just a good illustration that when you have periodic texture like this, and in this case, the RSM is about 0.7, if you want to capture that wavelength in your roughness profile, you need to use a filter cutoff that's larger than it. And often more than twice as large would be a good guideline. So on the next slide, Pat's going to walk us through some of the recommendations from standards. And these are tables that you can get from the standards. They're also available in our user manual in the software. So they're available there if you want to look it up and to help you choose different parameters. Well, Pat, why don't you tell us a bit about these tables and how to interpret them?
Yeah, these tables come right from the ASME B46 standard. So there's two tables. The first one is for periodic profiles, similar to the profiles that we just looked at. So if your surface has a lay or a texture or a repeating pattern, you'd want to use this first chart. And basically, you would eyeball, looking at the profile, you would visually try to determine that average distance between those peaks. You could use the software, you could use the cursors to try to find that, or you could just simply look at the x-axis on the chart. But once you figure out what that RSM value approximately is, you would look at the first two columns and find out where that falls, and then move to the right, and that would be the filter cutoff that you would probably want to start with. And as Kimo said, that filter cutoff has to be larger than that period, or you're going to filter it out. And so if you look, the filter cutoff that's recommended is typically about 2 times the size of the high end of the range. Now that's what you would do for a periodic profile. On a non-periodic surface, which does not have a texture, or I should say does not have a repeating pattern in the texture, you'd want to use the second chart. And the way that's done is you basically take an educated guess of what the RA value of the surface will be. Now, once you've been doing this for a while, you can have a pretty good guess of what it'll be approximately. And then you would use this chart to find out where, using the first 2 columns, find out where that falls, and then use that filter cutoff to start. So then you would take a measurement, look at the RA value, and make sure that it still falls within that range. If it doesn't fall within that range, you may have to change the filter cutoff accordingly, make it longer or shorter. Once again, I just want to point out that these are recommendations. This is a starting point. You're only using this in this situation where you don't know the filter cutoff was not specified on the drawing. So this is not set in stone. Depending on the functionality of your surface and the type of surface you're measuring, you may not use these values for certain. So this is a recommendation, not a law.
Great, thanks, Pat. This is a good starting point, but oftentimes it comes down to understanding a bit about the surface you're measuring and getting opinions from perhaps engineers who designed the part to understand the function, because that roughness value can impact the function. So we've talked a lot about this choice of lambda cutoff, how it puts some of the energy into the roughness and other wavelengths into the waviness, and you give some guidelines for how to choose that based on the content of the profile or of the signal that you're measuring. But what about this idea of direction? You know, what direction, where do I place the line? How does that placement affect the roughness results? So Abby's going to switch back to GelSight mobile software. We'll load a shot peen example. Here's an example of a texture that doesn't have an obvious periodic texture to it. And you know, if you talk to people who do roughness and measure it as part of their job, you hear all sorts of fairly common complaints like, well, every time I put the tool down, you're talking about stylus profilometer typically, I get a different roughness value. So how do I know what the real roughness value is? Or you hear processes that have been put in place to deal with the variability where they'll have to take 5 profiles and average them. But yeah, Abby, just, you know, why don't you put a profile down and show us kind of what you can see on a sample like this.
Sure, yeah. So I'm just going to add a profile roughness function the same way we've done it this whole time. And we can see the RA that's being reported here, 1.39. But as we move this, we're going to see that change. We're at 1.73, 1.4, 1.46. You know, so every time we move this, we might be getting a different number. And there are a couple ways that we can handle that in our software. So since we have this area-based scan system, we've got all of this other data we can work with as opposed to just having the profile. So one thing that we could do is change the profile count. Maybe we want to look at 21 profiles evenly spaced within 3 millimeters. And I'll click Analyze. So now we can get the average RA, which is the average RA of all of those 21 profiles. And we also see the RA, which is just the RA of that center profile. So as we move along, you'll see the average RA won't change as much because, you know, we're averaging a lot more data than we were with just the single profile, right? So you'll see we're in around 1.45 for that average RA. And even if we did something like this, you know, we're still looking at a very similar output there.
Yeah, I want to mention that this is a super powerful feature because I remember years ago participating in a gauge R&R study with a profilometer where we had to take repeated measurements in an area on a part and then record those RA values in an Excel spreadsheet and then move the profilometer to another area on the part, take 5 more measurements, record those values, move the profilometer to another area, take 5 more measurements. And it's a tedious task to do that. It was time consuming and you write the number in the Excel spreadsheet incorrectly, something can happen. But this GelSight system makes doing things like that so much easier. I wish we would have had this back then. That'd been great.
Yeah, no, that's great feedback. I mean, I've certainly done my share of profilometer measurements and have felt the pain too. A nice thing in the software as well is that you can save this as your default method for measuring profile roughness. So you don't have to choose 21 profiles and the gap each time. You could just set that up. And every time you do a roughness measurement, it's going to lay down those profiles and give you that value. So much faster and much more repeatable than a stylus instrument. We see a lot of power there. But what's really interesting is the fact that, of course, we have an area. So now we're taking 21 profiles, averaging them, but there's still a lot more data we could work with. And in our software, for at least a couple of years now, we've had the surface roughness tool. So Abby, why don't you show what that looks like?
Sure. So we've only talked about profile roughness up until now, which is just the roughness along a line, but we also have roughness over an area. So for this one, I'll draw a rectangle and I'll click Analyze. and there's going to be our surface roughness, so the roughness over the defined area here. So we've got an SA output as opposed to an RA output.
Yeah, just to point something out here, the SA and the RA parameters, even though mathematically they're very similar, RA is computed over a profile, as we talked about. SA is computed over an area, right? So people will often ask, the parts drawing has an RA call out or a specification on it. Can I just use SA instead of RA? And the short answer is no. Quite often, those numbers are similar. On a surface like this, that's what they call isotropic, there's no pattern or lay to it. Those parameter values are usually pretty close. But on a surface that has a distinct pattern or texture in it, that number tends to deviate a little bit more. So SA is not a direct, even though it's mathematically very similar, it's not a direct substitute for RA.
Yeah, and I'll say that when you're out in the field, especially talking to customers who are working on legacy components or are on, aircraft or other things that the drawings and everything was designed years ago, you'll see RA. That's the spec that's on the drawing. That's what they need to hit. And in that case, we would recommend trying average RA because it's still an RA calculation, but it does that averaging that people often do as part of their process, taking 5 measurements, throwing out some, averaging the rest. We've seen all those types of heuristics, and this just gives you a much more faster and repeatable way to do it. But in new applications, we think SA and the aerial parameters are really very interesting because they capture much more data, they can be more descriptive, and if you're not sort of confined to legacy specifications, investigating what these parameters can do for you and how they can describe the surface can really, open up a more repeatable and a better measure than the simple profile parameters. Great. So on this, I'd like to go to one more example, which is a great one that came from one of our aerospace customers. And it's a good illustration of having to understand what the specifications are and how they intend to measure roughness, because it wasn't obvious to us when we first got measurements from this part.
Yeah, so when we first received this sample, I took the scans and you see this texture here with this ribbed pattern. And my initial thought was that we should do, well, I already saved the default, so we'll do it like this, is that we should do the roughness in this orientation. We should perform the measurement in this orientation across these ribs. But what the customer is actually interested in was the roughness between them. So their actual application was the roughness in this orientation. So this is just an example of, it might not be obvious without the context of the application, what we should do in the software.
That's right, thanks. And I think that is the theme here, which is you can make some educated guesses. You can follow the guidelines and the tables, look at what the waviness profile looks like and try to understand, are you getting your roughness signal in that profile or not based on your filter cutoff, directionality, and other choices. But in the end, a lot of times it helps and it's important to understand the component, the customer's need, or talk to the engineer who's designed the component to understand why the roughness is critical, and that can advise the methodology for measuring it. So with that, that's the basic content we wanted to go over for this presentation, but we have a bunch of questions that have popped in. So we'll go through a few of those now. First question is it possible to record the session? So we are recording it, and we'll make this recording available. How can we be sure that we are perpendicular to the texture when we sketch the line? Well, we do have some tools that help with that. Maybe Abby can even demonstrate one of those.
Yeah,
I'll say, yeah, she's bringing it up. I'll say it's often not that critical that you're perfectly perpendicular to it. You obviously don't want to be orthogonal, but we do have a tool here that we can show.
Sure. So this does depend a little bit on, the surface that you're looking at. But we do have the ability, if there's enough distinct features, to find the edge. So if you have an edge or maybe a hole diameter, we could find that edge and then snap perpendicular to that. So for this example, we could do something like, if I draw this line, it actually snaps to the edge here. And then when I draw my profile roughness function, which actually we'll go ahead and reset the defaults here. But when I draw my profile roughness input, you can see it snap perpendicular along that line. So just like that. And we can use a tool like that to make sure that we are perpendicular to that texture if there's enough edge to find it.
Great, thank you. There was a question on what's the minimum resolution for the roughness measurement? So I'll take that one. Our GelSight Max tool is the tool that we recommend for roughness. We've done a lot of studies comparing the roughness results out of that tool against stylus instrument, particularly 5-micron tip on a profilometer. And on the spec sheet, we show that system, we've demonstrated roughness capabilities from 0.2 micron RA up to 20 micron RA. So it covers a good range. We also know that our Series 2 has been used by people doing roughness for additive manufacturing, which are typically much rougher surfaces. So it does come down to the wavelengths in the surface that you measure. Do you need the higher resolution GelSight Max device, or will the Series 2 be sufficient? We can help advise on that once we understand more about the surface that you have. Question on the statistics. We talked about average RA, and this question is, are there statistics for the average value? So Abby, what do we have in the software today?
Yeah, so right now we just have the average for RA, but this is something that we'll talk about a little later, just internally to see what we can add to the software in the future. I have heard a request for standard deviation, for example, or also min and max values too. So.
Yeah, no, it's a great question, because I think the ability to get access to all those parameters and export them, people could do a lot of different statistics on them that might be interesting.
And we can right now kind of do that separately. So I've only shown running one analysis function per scan, but you could run multiple. So we could add, a profile reference function, draw the line, add another one, draw the line, and then export all of that to a CSV file and do your analysis that way. Any of the other statistical analysis that's available in Excel or whatever you want to use. So it's obviously a little bit more manual that way, but still pretty quick compared to some of the other tools that are out there. You saw how long it takes to draw the line. So
yeah, that is true. All right, another question for you, Abby. If we entrust the measurement to non-expert users, is it possible to define pass-fail criteria?
Sure, yeah, we have that option in the software. I'll just pull it up, actually. Let me share the screen again. So I'll just go to configure here, and all of our analysis functions let you configure pass-fail outputs. So under analysis, we've got profile roughness, and maybe we care about average RA. We can check the pass-fail button next to that, and we could set min and max thresholds for any of these.
Great, thanks. This one looks like a good one for you, Pat. So, would you switch cutoffs after you get an RA or SA results to better fit the recommendation table? If we were expecting a 2 to 10 micron and set the 0.8 cutoff but got 11, should we reanalyze with the 2.5 millimeter cutoff?
Well, according to the table and the standard in their process, yes, you would change your filter cutoff and then reanalyze the surface and reevaluate to make sure your RA is now within that range. But once again, that table is a recommendation. It's not a law. So you have to make these decisions based on the functionality of the part you're measuring. So you have to know, you have to kind of intuitively know like what wavelength regime that you're interested in. So you don't want to be removing part of the signal from the roughness profile that affects the functionality of your part. But that if you follow the table, yes, you would change the filter cutoff.
And I think some of the examples that we showed that you talked about, Pat, we talked about looking at that waviness profile to help you make that decision. So you can look at your waviness profile versus your roughness profile, and if you see some of that signal there.
Yeah, you can get a good feeling just by looking at that waviness, the shape of it. If it starts to take the shape of the pattern of the surface, you're probably influencing the roughness profile too much. You're probably taking out information from the roughness profile that you really want in your analysis.
Great, thank you. So another question, additive manufacturing may be a domain where SA matters more than RA. What's our opinion? Well, I'll start and then happy to hear from both of you as well. I think we've had a lot of interest from additive, and actually I can talk about this publicly because there was a PhD student, I think at ETH Zurich, who got his PhD measuring additive manufactured parts with GelSight, looking at roughness and showing, the value of our measurements in that space. I think because it's a new area, that it's not constrained to, past decisions like RA and others. They can start to look into these parameters. And I'll also say that with our tools, we have an area of roughness measurement. We're making that kind of measurement available to the market, available to anyone who needs it. And that just opens up potential. So additive is an interesting space. We're definitely interested in working with people in that space, learning about those opportunities. Abby, you have any thoughts, any exposure to additive roughness?
Yeah, we've definitely had a few applications come up, and I think that a lot of people in that space know that RA might not be the best fit because, when you look at some of these surfaces, they've got, it really depends a lot on where you're drawing the profile. Some of these have different layers, and it looks more like surface roughness could be a better fit for a lot of these.
Yeah, and Pat, I know you worked in this space before coming to GelSight.
Yeah, I worked for a company that did what they call binder jetting. There's a lot of different technologies in additive manufacturing, and I know there's a lot of research being done on how to analyze the surfaces that these processes create, because they are unique. In the field or the technology that I was working with, binder jetting, you basically you spread binder or glue at a high velocity. It doesn't look like a high velocity, but on a microscopic scale, it's quite a violent interaction between the glue and the metal powder. And what that would cause was some really crazy looking surfaces. If you were to get in there with a microscope and really analyze it, you'd actually see, sometimes you'd see reentrant features, which you describe as like little caves in the surface, which are incredibly difficult to measure. I'm not aware of any measurement system that can measure a feature like that properly. But so it's an evolving, there's a lot of, like I said, there's a lot of research going on how to analyze these types of surfaces. So.
Yeah, but I'll say the area roughness, it is relatively new. I mean, do you know when this specs first started being made and when tools started coming into the market?
10 to 20 years ago, the standards started including the aerial parameters. But up until recently, they have systems that are so high end and so expensive that they were only, they were lab machines. They were hundreds of thousands of dollars, and it just made it impractical. Like to take a part on an assembly line to measure for quality, to take it to a lab to measure on this highly expensive machine, which may take a while because it's got to stitch a bunch of images together. It's just impractical. Until now, with the GelSight system, you can actually get an area scan right on the shop floor. You take it out there and take your measurement, and it makes it so much easier to compute these aerial parameters that I think they're going to become more and more common in the industry as people learn that it's a lot, how do you put it? It's a lot more inexpensive to be able to actually acquire that data.
Yeah, thank you. And that really is our view. It's like make this capability more available to people, available on the shop floor, out in the field. And we're hoping to see more uses of aerial parameters. They're better parameters for surfaces, a lot more descriptive and a lot more repeatable. So, we'll end it with that. We appreciate everyone tuning into this. If you're watching it online, thank you. Feel free to reach out with questions, and we're happy to tell you more about GelSight technology and roughness measurements. Have a great day.
Thanks.
Thanks.